Hi everybody and welcome back. Now it's time to build and train the Atrium segmentation model. Let us create our model class called Atrium segmentation, which inherits from pl.lightning module. At first, we define the initialization function, in which we call the superconstructor before doing anything else. Next, we create a variable called self.model, which takes an instance of our unit. As we directly implemented the unit for this particular task, we don't need to change any layers. After that, we define self.optimizer, which will take the Atom optimizer with the parameters of our model and an initial learning rate of 1e minus 4. Last but not least, we assign our previously defined dice loss to self.loss function. Alright, the initialization is done. Let us quickly define the forward function, which returns the output of self.model based on data, followed by the sigmoid activation function. Now we are ready to define the training step. As usual, it accepts self, the current batch and corresponding batch IDX. At first, we extract the cardiac MRI slices and matching segmentation masks from the batch. Next, we convert mask to float for loss computation. After that, we can directly compute the prediction by calling self and pass MRI to it. Based on this prediction and mask, we can compute the loss by calling our loss function, to which we pass the prediction and ground truth segmentation mask. Last but not least, we can log this loss with the identifier train dice. Additionally, let us again implement a log images function, which logs a slice and corresponding predicted label mask every 50 batches. Therefore, we at first check if the current batch IDX modulo 50 is congruent to 0, to finally call self.log_images, which will accept a batch of MRI slices copied to the CPU, the corresponding predictions and masks also copied to the CPU, and last but not least, a unique identifier. Let's simply use train. We finalize our training step by returning the loss. Alright, we implemented the training step. After that, let us copy this function to implement the validation step. We rename training step to validation step, the unique identifier train dice to val dice, and last but not least, the unique identifier in log images also to val. Additionally, let's log every second batch here. Alright, our validation step is also complete. Perfect! Now we are ready to tackle the log images function. Let's define it. It accepts, of course, self, a batch of MRI images, the corresponding predicted and ground truth segmentations, and last but not least, the identifier. At first, we threshold our predictions at 0.5. This means that every pixel that has a predicted value smaller than 0.5 is assigned to the negative class, while in contrast, the remaining pixels are assigned to the left atrium. Next, we create a 1x2 figure where we visualize a slice and its corresponding ground truth segmentation in the left plot and the slice plus predicted segmentation in the right plot. Let's use the first slice within each batch. Alright, we create a 1x2 plt.subplots object where we at first visualize the first slice of our MRI badge. Of course, we use either the bone or gray color map. Next, we create our masked array by masking all elements that are 0 in the first segmentation mask of our badge. We then visualize this mask over the current slice with an alpha of 0.6. After that, we plot the first slice again in the right figure. Create our masked array for the prediction. To finally visualize it. Last but not least, all we have to do is to add this figure to TensorBoard by calling self.logger.experiment.add_figure, which accepts at first the unique identifier called name, next the figure, and last but not least the global step. Alright, that's it. Our logimages function is complete. The last function we have to define is, as usual, configure optimizers. We simply return our optimizer packed in a list. Perfect, we successfully defined the Atrium segmentation model. Before creating an instance of this class, we call torch.manual_seed0 to fix the seed of the PyTorch random number generator. This results in the weights of the model being initialized the same each time. Please make sure to write this line directly above the instantiation of the model and in the same cell. If you miss this step and somehow create a new instance of the model, the weights won't be initialized the same anymore. After that, we create the checkpoint callback by using the model checkpoint class. Let us save the 10 checkpoints that have the lowest or minimal validation dice loss. We are now ready to define the trainer by using pl.trainer. At first, we define the number of GPUs we want to use, 1 in my case. Next, we set the TensorBoard logger as logger. As usual, we define the safedir to be logs. After that, we define the log interval, which I want to be 1. We pass our checkpoint callback to the callbacks and train the model for 75 epochs. Note that after around 20 epochs, you already get very good results. The remaining epochs, however, only serve to minimally improve the performance. Now we call trainer.fit, to which we pass the model and our both data loaders to finally train our Atrium segmentation model. Note that depending on your hardware, training might take several hours. We provide multiple checkpoints in the wait directory of this lecture so you can evaluate and validate the model without fully training it. Alright, let's go. See you later. Okay, perfect. In the next lecture, we're going to evaluate and validate our model. Thanks.